Hi everybody, welcome back. So in this episode we are going to work on the meter circuits and hopefully they will work. First thing I'm going to do is disassemble this board, but in order to do that I'm going to mark all these wires so that I know where they go and I'll take them off. It'll be a lot easier without the wiring harness to go ahead and do that, and then I can properly clean the wiring harness. Okay, I marked all the terminals here with numbers and then just took the white heat shrink and labeled all of them to match so we can remember. I also took pictures, but it's just easier that way. So the first thing I'm going to deal with is this fuse. Instead of using a pigtail fuse, I think I'm going to put these in here. And so we can put just a normal removable fuse in there. See if I can do that. And I will obviously have to modify the board slightly for that, but it shouldn't be too bad. All right. And what I want to do is I'm just going to mark this roughly where I want it as I drop everything. And we're going to have to drill an extra hole. So, and this one's going to go right through this trace, but that's okay, we can fix that. I'm just going to put a little scratch here on the board. That'll give us an idea of where we want to drill. Go right there. And I'm going to do the same thing over here. There we go. And then I could use a regular drill bit, but I think I'm just going to use a pin vise because I don't think this is going to be too hard to drill through. So let's do this one first. That's it. So there's one. And I might have to enlarge that a little bit, but that's okay. I can do that later. Okay. I should be able to put these in here. They might be a little bit too big. I might have to open these holes up a little more even. Yep, I will. That's okay. Okay, that's better. Now the next thing is I will replace these capacitors. There's 5 of them. That should be easy to do. And then I'm probably going to replace all of these transistors because if you see these, they have tin whiskers on all but these 2 with the gold leads. And I don't know. I think I'm just going to replace them. Okay, the board is done and cleaned up. Looks good. So let's put that aside. And I'm going to work on cleaning these controls. And I'm just going to thoroughly clean these, take them apart, and get them cleaned up, get the wiring harnesses cleaned up, put it back together. Okay, the controls are clean. And look, little shot of that electromotive, and this thing looks brand new. And the contacts are perfect on it. So everything cleaned up. Got the cover back from, all the covers back from the powder coater. And look at the job they did on this thing. Beautiful. It looks brand new. So time to look at some pictures and figure out where everything goes. And then we'll be right back. Okay, that went right back together. Looks good. And then here's the whole harness. I cleaned it up as best I could. It turned out pretty good. I'll have to disconnect these phone jacks here and replace them with the RCAs that are mounted in there. But I think we're in good shape. Everything went back together pretty well. Okay, time for the big reveal on the sides and the base plate. And the base plate's the one I really want to see. Let me get this off here. That's an annoying sound, isn't it? How's that for ASMR or whatever that crap is? Are you relaxing yet from the sound? All right, how about some more soothing sounds? There you go. Is that helping your circadian rhythm or your cicada rhythm? There. Okay. Wow. That'll do. All right, well, I sure hope this other one... Now, these are steel, but this one here is aluminum, and the process they do on this supposedly works really well on aluminum because they do a lot of aluminum automobile parts. And I'm thinking that this is going to look really good. As long as I don't gouge it with my pocket knife as I am opening it, because you know I have been known to do things like that. Yeah, you can imagine what I'm like on Christmas morning opening the presents, huh? Okay. Oh, I forgot. Here's the top. So here's the top piece. That's steel also. And that was completely rusted. Look how well they got this thing. It was rusted and it was pretty badly warped. And they got it really straight. Oh, I'm thrilled with that. That's great. Okay, let me set this down. And let's look at this now. Nice. I think that'll be good. That's a thick piece of aluminum. And that looks good. I'm very happy. We can get the transformer mounted back on here, and we can start putting all these pieces down. Excellent. Okay, things are starting to take shape here. The capacitors are wired up for the most part. We have the front panel installed, and I have the harness put back in place. And I kind of cleaned this up a little bit over here as best I could. Got the rectifier connected, and I'm getting ready to put the back plate in to see how everything fits. I think what I'm going to do prior to that, though, is I'm going to put the amplifier module in there, because really we're kind of tight for space on this fan, and I want to make sure I didn't shim it out too far. So I'm going to kind of just look at that first, and then we'll be back. We'll see what happens. Okay, we're moving along pretty good here. Before I show you the back panel, I do have the amplifier in the front panel mounted. All of the wiring is pretty much in. And I'm working right now on this fan system. Now originally, the original thermostats that they were using for these, the thermal switches, are set to kick in at about 140 degrees Fahrenheit. And, you know, that's closer to, I think, 60 C or something like that. These ones are 50 degrees Celsius, which is 122 degrees Fahrenheit. So these will kick in just a little bit sooner than these ones. And I think that's going to be helpful, because this fan is going to move some pretty good air through there. Once this thing gets hot, if it gets hot, that'll give the fan a little bit quicker response time. It'll also let it shut back down, because this fan is going to move so much air and get so loud that it'll cool it very quickly. So I don't want it to rapid cycle. The real goal here is for the fan never to have to turn on. So hopefully if we set the bias correctly and everything, as long as you're not pushing this amp really loud to the point you won't hear the fan anyway, hopefully that fan will never kick in. But again, I'm going to experiment with this. If it cycles the fan too often, I can always change these out for some bigger ones. So that's what I'm doing. That's my plan for the moment. It might change. Well, things are packed in here pretty tightly, so to make it a little bit easier to work on, these speaker terminals here are removable. And you can see the screws that you can just go down here and tighten them. And what I'm going to do is, you can see this stranded wire is very good quality, but it's stranded. So I want to make it fit in those little clamps a little better. Same thing here when you're dealing with these. So what I'm going to use is these ferrules. And there's different ones. These ones don't have the boot on the end. And I'm going to use those for these speaker wires. And they come right off of the amplifier module. And they just go on like this. So you just put them on the end, crimp them. You can see how nicely that crimps those on there. And what I'm going to do is get these all crimped, and I may have to use a couple that have the plastic sleeves on the end of them because I'm running low on these ones, but that'll still work. And then that's going to make it a little easier. If I ever have to remove this, I can just unscrew the terminals and it'll keep these wires from being messed up. The other thing is, when you use those screw down blocks like that, those clamps inside there will pinch onto this metal and kind of deform it. And that'll make it hold a lot better than just the loose strands that are going around in there. At least that's been my experience. So I'm going to do that, and I've already got the fan bypass, for the high speed, for the little thermal switches. I have those crimped on there. You can see these ones are going to go on this side, and then these ones go on this side, and then if either side overheats, and the switch will close, it'll bypass this resistor network here and put full power to the fan. At least that's the plan. And I had to grind off a little spot down here for the ground wires to go on the plate, because when they powder coated it, it covered that up. And I'll tell you what, it took me some grinding with a grinding wheel and a Dremel to get that paint off, or that powder coating off. Just can't believe how strong this stuff is, how durable. But which that's a good thing. All right, let me get this put together and get these put in, and I'll show you the finished product. Okay, well, here is the mostly assembled amplifier, and nothing has been tested or powered up yet. I really thought this was going to be a lot tighter back here, but if you look down in here, it actually looks pretty good. So you can see here's the speaker protect module. Here's the soft start module down here with the inrush current limiter kind of facing up, so it can kind of vent if it needs to, let the heat rise. Everything else kind of fit right in place where it used to be. This is your power switch wires right here coming from the power switch, and this is all your power terminals down here. And it's pretty much back together the way it was, other than this modification down in here I did. So I think I'm ready to just kind of make sure there's no shorts or anything anywhere. This should be pretty simple. I'm just going to take the meter and do a couple basic tests. Now, of course, this is going to come up on a current limiter. And because of the way this inrush current limiting, this ICL module works, or ICL, thermistor works, I'm really not going to have to do any jumpering anything out or anything to bring this up. I'm just going to connect it to a 100-watt bulb, let it come up really slow. If there's a short, the 100-watt bulb will take it. But I just want to make sure there's no shorts or anything. You can see that's just the capacitor charging. And if I go here, same thing. So there's no shorts. That's just capacitor we're reading. And that's really the main thing I'm worried about right now. Okay. So you're going to see this along with me. I am going to take a couple of probes here, and I'm just going to monitor my voltages as this thing comes up. So let me get those hooked up. Okay, it's pretty hard to get everything in shot here, but I have both meters connected up. This is the negative supply, this is a positive supply, and if something decides to go thermonuclear on us, I should see one of the voltages or both of them drop, and I'll see that light get really, really bright. So let's turn on the power. Well, first of all, how about I plug this in. There we go. And the power switch, I think, is on. This is one of those switches that's really hard to turn. I'm going to have to put the knob on. Let me find the knob and put on there. Hold on. Okay. Turn this on, and I don't know if the switch is turned on or off right now. We'll find out. Well, it was on. Oh, everything clicked in. Fan is running. Voltages are good. Bulb is not super bright, but it is bright. You can see it's lit up. And we're only running plus and minus 44 volts, which, remember, when this is at full power, it should be 80 some volts. But I think that's all we're going to get right now out of it. I don't see any shorts, but we're going to have to look at the outputs and see if we have any kind of offset. So let me check that now. Okay, you can never have too many meters, can you? So let's look at one channel. And we have about 121 millivolts. And on this one, about 112 millivolts. So we do have a little bit of DC offset, but it's not bad. Let's go to AC. I just want to make sure we don't see any kind of oscillation going on or anything. Nope. That one's clean. That one's clean. Okay. So I think the next thing I want to do is see if we can get rid of that offset. Now again, with this limited power on here, I really don't know if we can get rid of all the offset or not. But we'll try. We'll try to do some adjustment here. Okay. Let me get a non-conductive screwdriver. Hold on. Okay. We're going to pay attention to this one here and just see if we can get that to come down a little bit, or to change at least. I don't know. That's the wrong way. Hey, look at that. Huh. How about that? Okay. That amplifier's working. Or at least it's working from that perspective, you know. We can adjust the offset. Okay, so let's put on this one. Okay. And same thing here. Let's see if we can adjust it. Hopefully it'll do the same. Oh yeah. 1 millivolt. That's good for me. Okay. So now let's see if we have any kind of bias voltage on there. I'll have to get some different probes for that. Hold on. Okay, I'm connected across one set of the emitter resistors. You can see I don't have very much bias at all, but again, I don't want to have that much because I'm running this thing at just a little over half of its voltage. I just want to make sure it's adjustable. So if I turn this, it should change. And it does. See that? So I'm just going to keep that, you know, right around 5 or 6 millivolts right now. So that channel's good. It's doing what it's supposed to. This one probably will too. I'll get some probes on there and test it, but I think we have a functional amplifier right now. Let's turn power off. Great. So I heard this shut off, which was the speaker protect, and then I heard the relay drop out for the soft start, and you could see it bleeding the capacitor bank down. That's exactly what it's supposed to do. Wow, first time, and it worked. Usually there's some problems, but remember we did bench test this a little bit and did find that one bad resistor on the one module. But we're off to a really good start here. Okay, what a mess. So I have this meter just looking at one of the rails because they're identical. I mean, to the 1/10 of a volt, they're identical. I have this meter looking at this channel over here and this meter looking at this channel over here, just looking at the bias voltage. It's going to be somewhere between 10 and 30 millivolts, I would say. And what we're going to do is called a no-load test. And in order to do a no-load test, you don't connect any speaker load, any resistors, anything to the speaker terminals. So you're just driving the open speaker terminals. Now, before all of you folks out there that have been Googled start commenting, when you hear people talking about that you shouldn't run an amplifier without a load connected to it, they're talking about vacuum tube amplifiers. Vacuum tubes are very dependent upon the reflected impedance because of the output transformer. So if you drive a vacuum tube amplifier without a load on it, what's going to happen is the audio output transformer in the output section of the tubes will not reflect the correct impedance back to the tubes, and therefore you won't get the proper loading, and it could overload the tubes and damage them. In a transistorized amplifier, there is nothing like that. It's completely different topology. You don't have to worry about that. As a matter of fact, it is desirable to do a no-load test when you're first testing an amplifier, because if something goes wrong, you probably won't short out the transistors if something goes, if there's a problem in there. Whereas if you're putting out a lot of voltage onto the speaker terminals, you put a very low impedance load on there, like an 8 ohm resistor, you're going to draw excessive current through your output transistors. And conversely, that'll channel back through all the direct coupled stages and damage your amplifier. Quite often, if you're doing a no-load test, you can see the problem on your scope and on your meter long before it causes any damage to your amplifier. So again, on a transistorized amplifier in this type, from this kind of generation here, it's desirable to do a no-load test first. That's what we're going to do. So looking at the bias, I have the oscilloscope connected to the two outputs, where the speaker terminals would be, and there's no load on there, so it's high impedance. And then I have my little portable, that I'll turn on, signal generator. And it's turned all the way down right now, and it's turned off. And I have the current limiter still in there, but I am using the 300 watt bulb, which is not going to get real bright, but it will light up because this transformer does draw a little bit of current and so forth. So you could see it's just, there it goes. You can see it's not getting 300 watts bright. All right. Okay. So looking at our bias, you have 17 millivolts here and 12 here. Don't mind the plus or the minus. It's just I stuck the probes on there however they were. I don't care about polarity right now. I just want to see the actual. I don't want these to be, volts. They should be millivolts. We have 67 volts on each rail right now. And this can do up to, I think it's supposed to be 86 volts. So it's still running, only at about 70% or so, give or take, of what it should be. But anyway, let's go in here. We'll zoom in a little bit. Let me turn on the sine wave. And let's see if we get, and yes, we do. And I'm on 20 volts per division because there's going to be a lot of voltage on the output terminals because there's no load. And you can see right there is 80 volts peak to peak. There's 100 volts, or 120 volts peak to peak, and there it's finally starting to clip. And you can see how nice the waveform looks. So both channels, you can see left and right. I'll separate them a little bit. And you can see they're tracking one another perfectly. So they both have exactly the same gain. So the channels are matched to one another, and they are doing a very good job. So this is all great news because the amplifier is working like it's supposed to. Okay, now that everything looks pretty good as it is, I've turned this down. And we're going to switch over to full power. And we now have our 85 plus and minus 85 volts. And I found that setting this somewhere between 10 and 15 millivolts is where we want to be on the bias here. So if you go from, let's see here, and I'll put up a final schematic of all this when I'm done at the end of the series. We're going to do one more part after this video. We'll do all the testing of the amplifier and then listen to it. But you can see we have these test points here. T and U, R and S. Hopefully you can see those. And if you do the math, essentially what you're going to come up with is about 1 milliamp per millivolt if you go across either one of these. And these are in parallel, for power handling. So whatever amount of wattage is being dissipated by this line here, an equal amount or similar amount will be on this end here. They'll be very similar. And that's another reason for these resistors here, is to take up any difference you may have in gain. So it's not important to gain match these 8 transistors here. So at 1.5 milliamp per millivolt, if you set it to somewhere around 15 millivolts, and then you look at the amount of voltage that's across these transistors, they're going to each be dissipating somewhere. You want them to be dissipating around a watt, maybe 1 watt, if that, or less. Just enough for them to be turned on and idling. And again, between 4 big power transistors, that's really nothing. All it's going to do is give us the ability to have very low or no crossover distortion. That's really all I care about. The higher you make these things idle, the hotter the thing's going to idle at. You're just going to make heat for no reason at all, and we don't want that. So again, I'm going to experiment with this, but basically each of the 4 sets of test points, I'm going to set them somewhere around that 10 to 15 millivolt range. You can see this, they're a little bit high. I'll have to adjust them, and that's really easy to do. Let me see if I can get everything in shot here. So I can just come in here, and yes, I got this big long adjuster. I don't know why, just because it's silly. And it's also out of the way here. So going the wrong way here. So I'm going to do just maybe about Let's go right around 10 or 11. How's that? And then let me go over to the other side. If I can get in here. Excuse my armpit. I just don't want any big idle current or anything. That's close enough. So now what we'll do is I'm going to put a signal back in, and I'm going to turn this way, way down. Okay. I'm going to go way down to 500 millivolts, actually 200 millivolts per division. And I'm going to try to get rid of some of this noise here. Let's see. I just want to get rid of some of that. Not necessary. Okay. All right. Let's turn on our thing here. And let's just, I just want a really tiny signal. You can see how tiny it is. And you can see there is no crossover distortion, even at 200 millivolts per division. And that's really what I'm looking for. So you can see absolutely no crossover distortion. And that's just a tiny little signal. Right now we're looking at about 185 millivolts RMS. So that's just a very tiny signal. So if there's no crossover distortion there, we're just not going to have any crossover distortion pretty much. So it can idle at that real low current like that. And it appears transformer loss, idle current of the outputs, everything all told, it's drawing 1.4 amps. And that's including all the losses on the bench and everything. That's not bad. So there you go. Now I'm just going to let this cook for a while and see how it works. And then I'm going to probably end this video right here. Everything's working. So what I'll do is I'll put it together. And then we'll go ahead and in the next, which will be the last part of all this, I'm going to go ahead and we'll do all the tests on the amplifier. And then we'll actually listen to it to kind of evaluate how it sounds, and that'll be it. And then we'll be off to another whole bunch of projects, because what I'm going to do is I'm going to restore several amplifiers like this. So this is a Marantz. We did a Pioneer Spec 4. Over here I have this Sansui down here, the BA 2000. I have with the CA 2000 preamp. I have a Carver M1.5T, and I actually have two of these. And then I also have a phase linear 400 and a phase linear 700. And we're going to restore all of them. And then we're going to kind of see some of the similarities and some of the differences in them. So that'll be quite a few projects yet. Okay, before I end this video, I thought I would take some time to go over some schematics and do a little bit of comparison. Because I was a little bit curious. When I first opened this thing up, it's been a while since I worked on the Marantz 2500. And if you go back to that video series and you look at the amplifier section of that, it uses that same cooling tower or cooling tunnel design that this one uses. And at the very first video of this series, I mentioned that the amplifier is similar to the Marantz 2500's power amplifier. And what I found out after looking back at the schematics is they're two very different amplifiers. They both share that same cooling tunnel design, but that's where the similarities end. Of course, the 2500 uses a toroidal power transformer. This one uses a standard, EI style transformer. It's potted, but it's a great big, square transformer. But the bigger details is in the actual design of the amplifier itself. So what I did was I printed out the schematic for one of the channels from the 2500. And the first thing you can see right away when you look at this is on the outputs. Here's your quad outputs, just like you have 8 output transistors per channel on the 510M. You also have 8 outputs on this one. But take a look. You can see all the bases are tied together, all the collectors are tied together, and the emitters, joined together through emitter resistors. This is a very typical Class AB design. You have a driver for each of the NPN and the PNP, positive and negative half cycle, and it's Darlington connected, just like a standard AB amplifier. You have the bias transistor, or the what we call the VBE multiplier circuit. The transistor for that is mounted on the heatsink along with the transistors, the outputs. At the front end of the amp, you have your standard input pair like you see on most Class AB amps from this era. And one thing I noticed is they drew the schematic backwards on this. These two pins 1 and 3 on the input connector here are swapped. So really this wire should be connected here and this wire should be connected here. This is the actual coming from the the preamp circuit. It should go in here. This is the input of the amplifier. This is the wire or the signal that goes out to the overload protection board and so forth, or the overload sense board. Anyway, you have your current source, and you have your buffers and so forth over here with current mirrors. You have your overload protect transistors here with the diodes and all that. This is all very common to a lot of these amplifiers. You have your voltage amplification stage, and then it goes into your drivers and then to the outputs. Very typical. Just the voltages are a lot higher. The current capability is a lot higher than your average power amp. This thing, I think, was rated itself at like 250 watts per channel or so. So it's very similar power rating to the 510M. But moving over to this one, big difference. And I went over this schematic on an earlier part, but you can see you still have 8 outputs. But if you notice, only 2 on each side are connected to the rails. So you have your 86 volts positive going into these 2 that are tied together, and their bases are tied together. Then you have, as these turn on, they feed these secondary ones outputs, and they're closer to your midpoint, and their bases are tied together and driven by a different driver transistor. You see that? And so this is what they call the power stack circuit. And to me, this kind of reminds me a little bit of a Class H topology in a way, in that Class H really is not like this, because Class H actually modulates your rail voltage as the demand calls for it, and it helps the transistors run cooler. This is a similar thing, but these transistors are turning on and off kind of together. So it kind of splits it between them, the voltage drop, and therefore the power dissipation between them kind of splits up, and supposedly should make it run a little bit cooler, is kind of what I'm thinking. And again, this is just kind of how I'm seeing it. I'm not sure. But we'll test this all out on the last part of this series. I thought that was kind of interesting. In addition, whereas with the Marantz 2500, you go straight into your input pair, the differential pair there. You don't here. You actually have a buffer section right here. And it's a unity gain. Once again, all it does is it just converts, it's just for impedance buffering between the input and the output. And then that drives your differential input pair. You still have your current source and so forth. But if you go through the way this thing is laid out, clear up to this point, you're still in unity gain. There's no gain in any of this circuit. You're just playing around with the impedance and so forth. Again, here's your overload protect circuit. Here's your bias transistor, and it is on the heatsink just like this one was here. And then you come out and go into your pre-drivers, and then you go into your main drivers, and there's 4 of them instead of 2 of them because of the way this thing's put together. So the way this thing kind of divvies everything up between the transistors in that so-called power stack, to me is kind of unique. I really haven't seen this exact design in anything else. Now, I don't know why they never really used this a lot more after this. I mean, this amp is one of the few that I've ever seen anything like this. But we'll see if there's advantages to it. And we'll also see how it performs. But I just thought that'd be interesting to go over that. Now, last thing that I want to address is I had a couple of comments that I would like to answer. I think it would be easier than me just typing something in the comments section, because some of these things are good comments and I want to make sure I speak to them. Number one, the input here on the original amplifier, this was a 1/4-inch phone jack, and this thing was geared towards being mounted in a rack and being used, for a PA system or for a DJ system or in a dance hall or something like that, or live performance. Really wasn't meant, I mean, it could be, but just wasn't really designed from the ground up to be, a home stereo. So no one's going to use a classic amp like this for that purpose anymore. If anything, they're going to want to use it on their home stereo. So I converted this to an RCA input. This has a shorting pin on it, which is actually a pretty good thing for that type of application, to keep any kind of hum or anything from, entering into the amp. But really, if this is on your stereo rack at home, you're going to always have your preamp plugged into this. So you don't need a shorting pin anymore. So that's all that we've done there. I've just removed that and replaced it with a straight RCA jack. Now, speaking to somebody made the comment that it's no longer a Marantz 510M because of what I've done to it. Well, I really disagree with that. All the transistors in this front end are original. I only replaced the couple that were actually bad, and I replaced them with replacements that are identical, will perform exactly the same way as the ones that were in there. I haven't modified or changed this circuit in any way. Only 2 changes I made. Number one, I don't like this thermal switch. It's designed to drop out at 90 degrees C. You see that? I don't know if you can see that or not. So that is way hot. And if you have transistors dead short, which, by the way, when this thing came onto my bench, all but one of these were dead shorted. All 8 outputs and 3 out of the 4 drivers were shorted. So that proves that it can happen. If that happens, you're putting all your DC rail, especially if one side shorts and not the other. If both of them short, there's a good possibility that, that could blow the fuse. But if just one side shorts out first, all that voltage is going to go straight onto your speakers, and this is not going to do a hill of beans of good for that. Now, if the amplifier runs super blistering hot, this will open up and disconnect the speaker until the amplifier cools back down. But really, I don't care about that. That's what the fan and all that other stuff is for. So I removed that. All it is another thing in the signal path. And I replaced it. So this is a 1-for-1 trade with another set of contacts, except this time they're relay contacts. And this is what I installed. You can buy these little modules on eBay or Amazon or any number of places, probably AliExpress, and all those places have them. And it's nothing but a speaker protect circuit. The one that I'm using is the one that uses the integrated circuit. And this is the same integrated circuit that they use like on the Pioneers and so forth of that time. They're still available, and they just make it simple. There's a lot that these can do that probably aren't used by this, but So what this does, there's a couple things about this specific module that I like over some of the other ones. And there's the part number, if it'll focus. There you go. Can you see it? There. This thing just, the focus on this camera sucks compared to my old Sony camera. This is a Sony also, but anyway, you have the two relays. The thing I like about this is this part right here. This is the actual power supply. And these two pins, you just connect your normal mains right from the mains connector right into it. And so it'll run all the way from 85 volts AC up to 265 volts AC. So universal power. And that powers this. Most of these modules you buy require a very specific, like a 20 volt AC winding on your power transformer of your amplifier to power it. And that becomes a problem if your amp doesn't have that. Like this one doesn't have that. So this allows you to this can run standalone on its own. It's just a speaker protect circuit. All it has is amplifier in, speakers out. That's it. Nothing else. And it does all the rest. It gives you the delayed turn on so you don't hear the speaker pop when the thing turns on. It monitors for, DC on the speaker terminals. If you have anywhere above between a half a volt and a 1 volt DC on the speaker terminals, it will drop out the relay and protect your speakers. If you hit hard clipping, it'll drop the relay out and it will time itself till it doesn't see it again, and then it'll come back in after a delay, automatically reset itself. If there's constant DC on, it'll never let the relay pull in. It'll just keep it out and keep the speakers disconnected. So this is just an insurance policy for your speakers. And all I did was I wired one of these to the output terminal of each channel. And of course, this is a stereo board, so you only need one of these for a stereo amp. And just stuck it inside the case. That does not modify this. That does not change the performance or the sound of this. All it does is it protects your speakers if these transistors short out. So if you're not going to do that and you want to be a purist about it and you don't want anything changing inside your amplifier because you want it to be a shelf queen and you want it to look all original, build one of these. All this is a plastic project case you can buy on any cheap store and mount this inside of it. Put a set of terminals on, for the input and for the output, and connect it to your mains, and you have an external speaker protect. This is a great thing to even have on your bench if you're into servicing amplifiers and so forth. This will just ensure that if you have one of these amps, you go back a ways, I did a video on the Kenwood KR710. It had a dead short on one of the outputs, just what I'm talking about here. And if I would have connected a speaker to that, it would have put 32 volts right under the speaker terminals and fried my speakers. So it's a good thing to have when you're testing an amplifier. So again, that doesn't change this amplifier. The last thing I did was to add a different soft start circuit. Now the soft start circuit that's in this is pretty decent to begin with. A lot of them don't have one at all. The 300, the model 300, or 2500, I'm sorry, the Marantz 2500, it has a speaker protect circuit. You can see it right here. There's the relays, there's the little transistor that pulls it in, and it's controlled by some external circuitry on another board. But it does the same thing as this. And the soft start circuit is right here, and it's another very similar thing. It has thermostats also that control the fan and all of that. Very similar to what this one's doing. You can see your resistor right here. It's a big 10 ohm gigantic resistor. And you have this big relay that just comes in and it bypasses the resistor after the capacitors are charged up. It monitors the voltage on the capacitors. It's a very similar situation to what we have. This is a little different layout. This one, the way it works is they put, for some reason, a negative voltage. They come off of one of the AC windings here of T1 transformer, goes through a diode that's backwards biased. I don't think it matters either way, but okay. Goes through this 300 ohm 5 watt wire wound resistor and into the coil of the relay, and then that has a capacitor across it. So you have an RC time constant right here, and you have a resistance here because this coil has a DC resistance. So what this does is this delays the charging of this capacitor. The capacitor acts as a short until the voltage builds up, which will prevent current from flowing through the coil, or will minimize the current. Not enough current will flow to pull the contacts in. After the cap charges up, current will then flow through the coil full power and the contacts pull in. So really this is totally dependent on this capacitor for when it comes in. Whereas the board that I put in place of this circuit goes across the capacitor bank between the minus 86 and plus 86 volts. So all 172 volts goes into this board and is split up amongst these two resistors here. And then that goes into this coil. So when the capacitors, these caps become your time constant instead of a separate cap. It's just kind of cool because if the voltage never comes up on this cap bank, on either one of them, doesn't come up far enough, the relay will never pull in and your resistive element will kind of stay in the circuit. Now on this one, just to save on size, I installed an SL32 inrush current limiter. So this is probably about an 11 or 12 ohm resistance when it's cold. And it's just enough to take the edge off of your incoming line when this thing turns on. As the caps charge up, they hit that certain level. Before this can even heat up and drop its resistance, which is what these normally do, you would just leave this in there, your relay will pull in and bypass it. That's all that I'm doing. I've gone over this 100 times on other videos, but everybody always asks every video, can you please show me how the soft start circuit? So I'm just explaining it again. It's a very versatile circuit. I made this little board just to hold the parts. You can see there's not much to it. And you can use any of these MY2 relays, which I also use for speaker protect relays because they're used a lot in amplifiers. And you can use a 48 volt or a 24 volt. These each will have a different DC resistance for the coil. So that's going to affect the resistors. And to determine what these resistance of these resistors needs to be, you have your total voltage is going to be 172 volts between your plus and minus 86, if I'm going to put it across here. Pick which one of these you're going to use, like let's say 24 volts. If you take 172 volts minus 24 volts, that gives you the amount of voltage that these two resistors here have to drop. And I'm splitting it up between two resistors so that the relay coil is in between the two resistors, number one, and it also spreads the heat that these are going to have to dissipate because resistors convert power into heat, electrical power into heat power. So that's how they operate. That's how this operates too. That's why you don't just leave this in the circuit. A lot of people are like, why don't you just put the ICL in there and leave it there? Because this will get blistering hot as it's operating. All that heat is going to be trapped inside the amp, and it's going to be a lot more heat than these resistors are going to. These are going to get warm to the touch if you put the correct ones in there. This will get so hot it will leave skin on it. Trust me, we use these all the time at work, and they get really, really hot. That's how they're supposed to work. That's what causes the resistance to go down. They're a negative temperature coefficient resistor is really what they are. So you can see we can use whatever voltage we want. Use Ohm's law to calculate the resistors. You can determine what current this relay coil needs by measuring its DC resistance. So for instance, this relay here is a 24 volt relay. So we know it needs 24 volts. It has a 631 ohm coil. If you take 24 volts divided by 624 volts divided by 631 ohms, you have 38 milliamps. So you know that this circuit is going to have 38 milliamps. You also know that if you take 172 volts minus 24 volts, you're going to be dropping 148 volts across the resistors, or the resistance that you have to put in there. And if you divide that by 0.038, which is your 38 millivolts, it means you need 3.89K resistance. So you need about 4K of resistance. So each one of these should be a 2K resistor. All right. So if you have 2,000 ohms times 0.038, that's going to be 76 volts for each resistor. And if you times that by the 0.038, it means it's going to dissipate about 2.9 or almost 3 watts of heat. So you want to have at least a 7-watt resistor in there. You want to have at least double the wattage that the resistor has to dissipate. And remember, if you put a 7-watt resistor in there, they're going to run pretty warm. If you put, like I put an aluminum 25-watt resistor, 2K on each one, and they're not much bigger than that, and they get warm. That's it. They don't get real hot. But that's how you calculate it. If we did a 48 volt, you can see the resistance will be different. And see, that one's 2.4K. So it's a lot higher resistance. And if you take 2400, if you take 48 volts divided by 2400 roughly, you only have 20 milliamps. So it's like half the current. So this is going to draw half the current. You have a much lower voltage drop, much lower current, much smaller resistors if you go with this. See how it works? It's all math. So you start out with, you can just use one of those little proto boards, do the math, pick the appropriate relay for what you're doing, and there's your inrush current limiter. And again, once these relay contacts close out, this whole circuit doesn't exist anymore. You're basically allowing the full power to go into your transformer. And again, it will not affect the amplifier. So when somebody made a comment that I'm changing the amplifier and it's no longer a Marantz, well, I don't know. I guess you could say that. I mean, I removed the horrible rust from it and repowder coated it. I'll show you the bottom of the amp here. I'm not showing you the whole amp on purpose. We're going to reveal on the next one. But let's look at this corner right here. This is unpainted because I didn't want to change the screen painting on the back of the back panel. Here is the new paint. Can you see where these transition to one another? Can you see any difference at all in the color or even the texture? It's identical. It's exactly identical. So again, I put new feet because the old feet were replaced anyway. They weren't the original one. The knobs were missing. This amp was in terrible condition. Hardly a shelf queen, hardly something that's can be kept original. So much of it was damaged and rusted and broken and worked on and so forth. So when you say things like that, you have to look at the context in which you're doing, and you also have to look at the purpose. Is this amp going into a museum, or is it going to go on somebody's stereo rack and sound the way it did 40 years ago? I mean, that's really what we care about, isn't it? We want it to perform the way it did 40 years ago, but we also want it to be reliable and be able to look good on your shelf. All those things. It's a lot more goes into it than just it's not original. Nothing's original anymore when it's that old. And when it is, you probably don't want to use it because it's original and you don't want it to change. You want to keep it as an example, for historical purposes. That's something totally different. So I hope that speaks to that a little bit. Now again, I also had to replace the output transistors. And again, I used ones that are more robust than the original ones, but as far as performance, they're the same. You won't know the difference. So I hope that answers all the questions. And with that, I'm going to end this part. And as always, I'm going to end by wishing you all peace, joy, happiness, and good health in your lives. And like I said, the last part, we're going to do the actual testing of the amplifier. I'll give it a listen. I'll let you listen in through the microphone and through YouTube and everything, so you won't really be listening, but you'll get an idea anyway. And, well, I showed you earlier here all this stuff coming up, so you can be looking forward to that too. And then maybe we can just kind of compare some of these. I won't be able to do A, Bs because I don't have room on a bench and time to do all that, but we can kind of progress through and kind of see the similarities of all these things as we do each one of them. So that's it, everybody. We'll see you again real soon. Take care. Bye-bye.